Coulombs Law. We've seen that mathematically Coulombs Law is expressed as we'll put a little E for the electric force, because that's what it is, expresses the electric force. And it equals K times Q1 times Q2 divided by R squared. So if we draw a little picture, just to kind of understand what that means, if you have a charge Q1 and another charge Q2, and they are separated by a distance R, then they will feel a force between them. Now, we'll have to talk about the direction of that force in just a second, but for now, I just want to point out why R again. It's just like with gravity. If you put a force here, let's call this Q1, well then Q2 could be anywhere a distance of R away, which basically means that it could be anywhere on this circle with radius R. So if we were to put Q2 over here, then we would see that it would experience a force, and the direction of that force would be along this linear line. But of course, Q2 could go anywhere on this circle and still feel the exact same force. So that's why we use an R for the distance between them, because it makes us remember the fact that we're talking about anywhere in that circular region. And in fact, this is only two-dimensional. We could extend this circle somehow. I'm not sure how you would do it, but you could extend this into a spherical shape, and so you would have anywhere sort of like around this shell, right? You could be coming out of the board towards you the same distance R. So it's not just a circle, it's actually a spherical area all around Q1 where you get the same magnitude of electric force. But that doesn't mean that you get the same direction. Let's talk about how we do direction now. Plus and minus. If we simply take the equation, what it will calculate for us is a magnitude of force. It doesn't give us the direction instinctively right out of the equation. Let's look at what happens if I do two different examples of this. If I do K and I do a positive Q times a negative Q, negative charge and positive charge, then the answer to this will come out to be a negative number, right? Plus times minus. But we know that positive charge and negative charge attract each other. Opposite charge attract. So a negative charge then would indicate an attraction, or a negative answer, sorry, between the two objects. So if you get a negative answer for this equation, that indicates attraction. But that attraction could be left or right or up or down, right? We'll draw a picture in a minute. Let's look at what happens if you did another example, but this time a positive Q and a positive Q, two positive charges. Well, then the answer that you got would be a positive number, and that would indicate a repulsion, because like charges repel. And the same would happen if you had a negative Q and a negative Q, right? It doesn't matter, as long as they're the same, you would still get repulsion. So when we use this equation, we have to remember that a positive answer indicates repulsion, and a negative answer indicates attraction. And then we can infer from the context which way that would be going. So if I draw my little picture again with Q1 in the middle, and I put the circle all around, and we put Q2, say, here, and we got a negative answer, which would mean attraction, that would indicate that there would be a force on Q2 this way and a force on Q1 this way. The electrical force between them would be the same force on both charges. We could say the charge on Q is left, the charge on Q2 is left, and the charge on Q1 is right. But of course, if you put Q over here, Q2, well, there's still an attractive force between them, so you still get the forces pulling in, but look, the direction now has changed. And so what we usually do is we rotate our reference frame to simply be the line between the two charges, whichever way that might be. And then we use basically left and right to figure out which way we want to go. So you basically infer from the context which way the force is actually directed. So it's a vector, it's a force, but the positive and negative answer you get from the little formula does not tell you the direction precisely. It only tells you attraction or repulsion. Okay, so we'll do an example, and we'll see how that will work. All right, let's take example number 1, which will be just plug and play. One other thing I have to tell you before I do the example, and that I can tell you while I do it. A 7 microcoulomb charge. That's what I was going to explain to you, how the microcoulomb thing works. So just give me a second. A 7 microcoulomb charge is 0.3 meters away from a -4 microcoulomb charge. Calculate the force between them. And of course we would mean the electric force. So that's kind of understood. Calculate the force between them. The microcoulomb is just a unit. A coulomb is like any other unit. It can be applied with the metric system. So you could have a kilocoulomb or a centicoulomb, but those are very odd units that just don't seem very practical. Because the coulomb of charge is such a big unit, 1 coulomb is big, so the typical charges that you see on things, typical charges, tend to be very small when we're doing questions and problems, and even in real life. And so a microcoulomb is simply 1 times 10 to the -6. It's a millionth of a coulomb. So whenever you see the word, the little micro, whenever you see that, you have to change it to 1 times 10 to the -6 in the formula, because we need coulombs in the formula, we need standard units. But you'll often see it written like this in textbook questions and so on, but you have to remember to do that conversion. All right, so there's 2 charges, 7 and -4 microcoulombs. Let's draw ourselves a little picture. Oops, getting weird lines. Let's draw a little picture. And again, we'll just set it up linearly, left and right. Here is 1 charge, and here is the other charge. 1 charge is, we have to check the signs. 1 charge is +7, and the other is -4. So we'll just choose that the +7 will go here, and the -4 will go here. And that's the reference frame we look at it from. But you can easily flip it around, it wouldn't matter, as you'll see. Okay, and the distance, I think, between the 2 charges, the other thing is, I should point out, is these distances are measured from the centers of the charges, technically. But because charged objects are relatively small, the radius of the object is usually insignificant, so we don't worry about that extra little bit of radius. We just consider the distance to be between the 2 centers. When you're dealing with gravity, we have to worry about the radius because Earth is huge and the radius is huge, right? But for tiny little balls and things that might get charged in questions, not so worrisome. So I think it was 0.3, was it not? The distance between the 2 objects. All right, let's plug in and see what happens. So F equals K Q1 Q2 divided by R squared. Be careful that your subscripts and your exponents don't get messed up here. There's lots of 2's on the bottom of things, and there's also 2's on the tops. 9 times 10 to the 9. Remember that from the other day? That's the value of K, right? Coulomb's constant. Multiplied by the 2 charges. And here's where I'll make the conversion from microcoulombs to coulombs. So it's 7 times 10 to the -6 coulombs for the first one, and -4 times 10 to the -6 coulombs for the second one. And then we're dividing all that by 0.3 squared. So we have to carefully crunch out this number. So let's do that. And if some of you do it with me, then we'll have confirmation. 9 times 10 to the 9 times 7 times 10 to the negative 6 times 4 times 10 to the negative 6 equals, divided by 0.3 squared. 2.8. And of course it will come out to a negative 2.8 because of the negative charge that we put in here. And it would be newtons. It is a force. So what does the negative mean? Well, the negative in this case simply means that the force is a force of attraction. So we would have to go back to our picture to decide which way that actually is. All right? And we realize that it depends on which charge you're looking at. If you're looking at it from the point of view of the 7 microcoulomb charge, it would be an attraction, so a force to the right. But if you were looking at it from the point of view of the negative 4 microcoulomb charge, it would be an attraction or a force to the left. So it's a negative direction for this one, it's a positive direction for the 7. You just have to tell from the picture, not from the negative. Okay, any questions about that? Pretty straightforward, right? All right, let's add another step in here. You know what? Put the subtraction?
Like, no, put his contraction.
Oh, not necessarily. Depending on what the question is asking for. This question didn't specifically say. All it said was, what is the electrical force between them? Right here. So it didn't specifically tell you which reference frame to pick. So in other words, we're really only concerned about the magnitude. It's 2.8 newtons of force between them. If you were applying that into a question, as we're going to do in example 3 later, where you have to actually use the electrical force with other forces, then you have to decide on your direction. Okay. So, example number 2. Let's say we have a tiny object. Let's call it a tiny ball of dust ball. And we'll give it a mass this time, 0.003, 3 grams of dust, kilograms, right? Dust ball has a charge of 6 microcoulombs. If it is 0.4 meters away from another charge, the second charge of 3 microcoulombs, how fast is it accelerating? Or maybe a better way to put that is, what is the acceleration? What is the rate of acceleration? And we'll specifically say of the 6 microcoulomb charge, so we know which one we're talking about. Okay, it's the same idea. We have 2 charges. We can put our picture here. One is 6 and one is 3 microcoulombs, 0.4 apart. So we can arbitrarily set it up here, 6. And the other one is 3, so we'll put it over here. And they have a distance of 0.4 apart. And we'll crunch out our formula. The electric force, K, Q1, Q2 divided by R squared. So 9 times 10 to the 9 for K, 6 times 10 to the negative 6 multiplied by 3 times 10 to the negative 6 divided by 0.4 squared. And do the math here. 9 times 10 to the 9 multiplied by 6 times 10 to the negative 6 multiplied by 3 times 10 to the negative 6 and then divided by 0.4 squared, I think comes out to pretty close to 1, doesn't it? 1-ish newtons of force. 1.01 or something like that. Close enough to 1. People get excited when things equal 1, but 1's a number just like 27.4. So it doesn't really matter. We're not quite done though, because they asked for the acceleration. That's the amount of force. Now in this case, if you recall, good old Newton says that the net force is equal to ma. You can see where we're going with this. In this case, the net force is the electric force. So the electric force is the only force acting, equals ma. So we can, let's erase that. We can plug in the numbers we need. The electric force is 1 Newton. And the mass was 0.003, right? Kilograms. And we're trying to find A. So 1 over 0.003 is A. How much is that? 333.3 meters per second squared. Very fast acceleration. Very high rate of change in speed. I should point out, when we're doing questions like this, when you have two objects, we figured out that this acceleration is the rate when they are 0.4 meters apart. But if you look at the equation for this electric force, you'll notice that as they get closer together, let's say a little while later, it's here, that makes a much shorter space between them, and this number gets continuously smaller as they approach each other, which means the value of the force continuously increases as they get closer together. So this is not a state where we have a constant acceleration. So the object doesn't accelerate at 333 all the way until it collides with the other object. It continuously accelerates faster and faster and faster because of the increase in force, which makes it a little bit trickier. Okay, any questions about that? Very straightforward. Now we're going to throw in the wrench, and we're going to describe a problem that's going to require us to use all of our knowledge about forces and everything we've learned so far. Emily's a little upset about that, but we're going to do it anyway, and it's going to be easy once you see how it works. So let's set up the question. Here is a spider web. Here is a spider on the edge of the spider web. You may ask yourself, why is the spider sideways a little bit? Well, it's because he's attached to a wall, and it's not windy. It's a very calm day. But through some series of events that remain to be explained, this spider has a charge. The Q on the spider has a charge of about 2 MicroCoulombs. And there's also a charge on, I'm going to call this the wall here, so you know what that is. He's against the wall, see? You can even make some little bricks if you want. There's the wall. Okay. And there's going to be a charge on the wall as well. Somehow the wall got charged, and we'll call that 1 microcoulomb of charge on the wall. Both positive charges. All right. Other information I'll tell you is the spider's mass is relatively small. It's going to be 0.005 kilograms. And what we're going to do is we're going to have two questions. Part A is going to be, what's the tension in his spider web? And the only reason I'm doing this as part A is to help you with the steps of the problem. And part B is going to be, how far from the wall is the spider? And I'm going to give you one more piece of information. How far from wall is spider? And by that we mean this distance right here directly from the wall. So we're looking for that. The other bit of information I'm going to give you is that there's going to be a 10-degree angle between the web and the wall. 10-degree angle. Okay, when you have a problem like this, it's not just obviously plug and play. What we have to do is we have to study it with our net forces, just like we did with all the other questions that we tackled. The only difference is now we have a whole new force to throw into the arsenal. Along with normal force and friction force and applied forces and gravity force, we now have electrical force. So let's start with a free body diagram. That's probably the best idea. So here we go. We'll put the spider web here, and here's the spider in the middle. The spider web is a rope, so it will have a tension pulling on it. The other force that acts on the spider would be the force of gravity, straight down. And if we go back to our picture and look at the electrical force, since both the spider and the wall have positive charges right here and here, there will be a repulsion, which means the electrical force must be pushing outwards on the spider. He's repelled away from the wall. So the electrical force goes straight out from the wall, I'll do it in a different color to keep it straight. Puts it this way. So here is my electrical force, Fe. We look at this picture and we see that two of these forces are nicely lined up with our x and y axes. Gravity and the electrical force are not a problem. However, the tension is on an angle, and we can't deal with an angle by itself. We have to do our little trick of resolving it into its components, right? Because remember, our strategy is to look at F net x and F net y. So for the tension, we have to kind of look at two vectors, one this way and one this way. This will be called Ty, and this will be called Tx. And since we know, if you look at the picture from before, what the angle is between the vertical wall is 10 degrees right here, we know that Ty will actually be T, and this time it'll be cosine 10 because it's adjacent to the 10-degree angle that I'm using. And Tx will be T sine 10 because it is opposite to the angle that I'm using of 10 degrees right there. So far, so good. Now remember, at this point, the black tension line is now gone from our perspective. We don't care anymore about it. We've changed it into two green lines instead. Let's do F net x's and F net y's. Well, for part A, we can do part A using F net y. So I'm going to start with F net y. So this is actually the solution to part A, finding the tension. If you look at F net y, you see there's only two forces. There's an Fg down, and there is a T cos 10 as the other component, right? The Ty. Now think about this spider. He's not moving. He's perfectly still, suspended from the wall, probably mildly upset about it. You know that feeling when you have when you take clothes out of the dryer and you're all staticky? He probably feels like that. It's very uncomfortable. He's not a happy spider, but he's not moving, he's not accelerating, so we can make the assumption that the net y force must be 0. This will be mg, so I can put in his mass of 0.005, multiply it by 9.8 mg, and remind myself that this red arrow is pointing down, so I'll add a negative sign to show direction. And then over at the other one, the T cos 10, can't see it in the picture, but it's right there, the vertical force. I can figure out the cosine of 10 degrees, and if I do that, it comes out to about 0.98-ish. So let's put in 0.98 T. And you can see that we can solve this, can't we, for tension. If we multiply this number, we get a negative, and I think that's going to be 0.049, right? Am I correct on that? Yeah, we're good. And we'll move it to the other side. I'll just finish this over here. We'll move it to the other side, making it a positive number, adding it to both sides, 0.98 T. And of course we divide. What do you get when you divide that? .049 divided by 0.98. It's a very small number, 0.05 newtons of tension. in the spider web. It is a spider web after all. Right? Apparently stronger than steel, pound for pound, but still very thin. So that's the answer to part A. What's the tension in the spider web? Now we needed that to answer part B. So if you were writing a test and they didn't give you part A, they just said figure out the distance between the two, you kind of see now that sometimes you have to do a little other work first to get information that you need. So I've set it up this way to kind of guide you. All right, let's look at part B then. And guess what? Part B can be addressed by looking at the F net X. In the F net X, if we go back to the picture, we have two forces again, a TX, T sine 10, and an FE, electrical force. All right. So the electrical force, FE, and the T sine 10, or the TX. But since the spider is not accelerating, and it's hanging there, the F net X is also 0, and this will be K Q1, Q2, over R squared. So we're simply using our new formula in place of the FE as a new force in the mix. And we have to decide now about directions. This is where things get a little bit weird with the plus and minus. Let's get the T sine 10 first. That would be 0.17t. Now, let's look at our picture. The electrical force is over here, and it's pointing to the left, which means that in our net force equation, it has to have a negative value to show left. If we go back to the original picture, we see that the two charges are the same. They both are positive, not the same, but the same charge, both positive charge, which means repulsion, which is how we figured out that it was going to the left in the first place. So we've already accounted for the repulsion, haven't we? We already know that if you were to multiply this together in the formula, you'd get a positive number that would tell you it's repulsion. But now we have to decide which way that repulsion is actually going to go. So what we need to do is we need to put a sign in front of this that will give us the actual direction, which is left, and the negative sign. So in our next step, we're going to put in the negative sign to show that this is all to the left. 9 times 10 to the 9. So the way to think of it is do the magnitude of this only. Right? I'm not going to put in pluses and minuses for my charges at this point. I'm just going to put in the magnitude of the charges because I've already figured out which direction they're going. And they were 2 microcoulombs, 2 times 10 to the negative 6 for the spider, and the wall, I think, had a charge of 1 times 10 to the negative 6 microcoulombs. And what we're trying to figure out, of course, is how far away you are from the wall, the spider is. So if we multiply the top of this out, we get 9 times 10 to the 9, multiplied by 2 times 10 to the negative 6, multiplied by 1 times 10 to the negative 6, equals about 0. Oh, sorry, I forgot something, didn't I? I wonder what happened. Let's not forget about our little plus 0.17t. He didn't disappear, he's still there. So we have to keep him in the picture. Now we can continue. Negative 0.018 is the number I got. And you can see here that we're going to get a tension of something very close to 1. Move that over, and you divide that. It's going to be slightly bigger than 1. Oh, actually, no. There's.
What happened to the R? Mine just put in 0.09.
Oh, there's an R there too. Yeah. Good point. We lost 2 things.
Then we already have T.
Right?
Then don't we already have T?
Yeah, you're right. We have T for the part 8. It's a good thing you guys are on the ball. So, well, you know what? Let's just reverse. Because if you watch this later, you're going to be like, what the hell just happened there? So let's go back to here. Before the teacher lost it. We had this equation. Everybody was happy, right? We had this and that. We got that. You're right. We know T, the tension, because we already figured out in part A what the tension was. It's right over here, 0.05. So that's what we were going to do. We were going to substitute that in. All right, so we get 0 equals, and this was 0.018, all right, over r squared. And over here, we want 0.17, not a plus, or not an equals, a plus. 0.17 multiplied by the tension, which we got over here. We'll double check it again. 0.05, good. That's where we should be. So we can do that multiplication as well. And what we get is, and this is a negative number too, let's not forget that. There's the negative sign. So 0 equals negative 0.018 over r squared plus this number of 0.005-ish, 524, but we'll just keep it at that. And then we want to move one of these to the other side. Let's move this one so that it becomes a positive number over r squared. And then we want to, I'm just going to do it here beside, we multiply the r squared over to the other side, so r squared multiplied by 0.005, and then we have to divide, so it would be 0.018 divided by 0.005 equals r squared. So we do the division and take a square root, and I think we're on the right track. Numbers wrong?
5, 8 plus 5 times 7.
Where are we that's wrong?
Those 0, 5.
This one?
Yeah, come back.
My calculator just doesn't seem to cooperate. It's one of these phones. It's stupid. I want a real calculator. You're right. Another correction. Rats. Well, this live video, that's what happens. 0.0085. All right, so we correct this. We multiplied these numbers incorrectly. We're here. Now we have to go back and do all that again, which we'll do from scratch because there's no point trying to fix it up. Let's try again. Okay, 0.018 over r squared, move it to the other side, equals 0.0085, correct? So far, so good. Multiply the r to the other side, r squared that is, here. Then divide 0.018 divided by 0.0085 equals r squared. Now divide and take a square root. And I'll try it, and you tell me if I'm right. 1.45? 1.46?
Yes.
You sure? That's a pretty big R. It's not very realistic, is it? It's like a meter. But nonetheless, we didn't set the question up to be totally realistic. We just set it up to show you how to tackle a question like this. So let's just recap that one, because we got a little confused at the end. Let's go back to the beginning, look at the question again, to make sure we understand what happened there. We had a spider on the wall, or sort of out from the wall. There was an electric force here. This was the electric force repelling him out from the wall, 10 degrees, and all this information. So we set up a free body diagram showing the three forces involved: the force of gravity, the force electric, and the tension in the spider web. A lot of people forget about the tension in the spider web. But you have to have that because the gravity force and the electric force are at right angles to each other. They have no effect on each other. So you can't put them together in any way. You need this tension force to be the link between these two. We resolved the tension force into its components, which is what we would have done before, so nothing new there. Then we set about doing two equations, F net y, which is here, which allowed us to calculate the tension, which is here, in the spider web. Then we went to F net x, and this is the one where the electrical force came into play. I just went too far. There it is, F net x, and there's our electrical force. we decided that that electrical force would have to be negative because of the direction it was pointing on our picture, because of the repulsion caused by two charges that are both positive. So we had to kind of get that negative sign. It didn't just come out of the math like you would expect for other things. Then we went down here, and we realized that we could substitute in the tension that we calculated from part A. So there it is, and that's where we kind of went nuts. But the real thing after that was to just algebraically work this out and work it out correctly so that we got the right numbers, and the rest of it is just working out to get R. So without the calculator errors, it actually wasn't that bad. So this is an example of how you can now use the electric force in with all the other stuff. And the questions in the book that I'm going to refer you to now will involve questions sort of like this, some of them anyway, so you've been prepared. And there will be future videos with future examples of future situations, but I want to give you a chance to tackle them first before we just start taking them all up and showing you how to do it. Okay? So that's the end of that.